Thanks. Okay, hi everyone. Thanks for being here. And I'd like to thank the organizers for inviting me. It's been really nice. I've learned a lot. So I'm going to just start on the blackboard and tell you a couple of things about the technique of scanning tunneling microscopy. And so I'm giving two lectures. Today's lecture is sort of an illustration of the kinds of things you can do with STM. You can do something called quasi-particle interference, you can do Landau level spectroscopy, and I'd like to illustrate those techniques using a very simple system, which is a topological crystalline insulator, and I'd like to show you how you can get really beautiful information using these techniques, okay? So today is that, and then tomorrow I'm going to actually talk about topological superconductors. And I'm going to try to give you two example systems. One is a proximatized topological insulator, meaning a TI proximatized with a superconductor, and that's actually iron selenium tellurium, FeSETE, so I'll talk about that. And then I hope I'll have enough time tomorrow in that 1 hour to show you some data on this new superconductor called uranium ditelluride, which might be a chiral P-wave superconductor, or at least it shows all signs of being a triplet superconductor with broken time reversal symmetry. It's got some complicated order parameter, but a triplet superconductor with broken time reversal symmetry, given the symmetries of that particular crystal, it seems likely that it might be topologically non-trivial. So in that case, it should have these Majorana edge modes. But this is a three-dimensional material, so the boundaries of this three-dimensional material are two-dimensional surfaces. So we'll see what we see using STM on this interesting new superconductor. So that's for tomorrow, okay? So let me just start off with scanning tunneling microscopy. The first part, and this I'll go through really quickly, is I want to just motivate where, we always write down this formula for what we measure with STM. And the formula looks like this, the density of dI dV, and I'll define everything in a second, equals sum over, whatever quantum numbers you want to use, squared. So this is dI dV at some energy E. Okay, so this is what we write down for what we measure with STM. So what is all this? Well, these are the wave functions of all. This is the wave function of a state at this energy U. So it's the square of the wave function. And so this is telling you whether a state exists or not at that energy with these quantum numbers. So basically, you're just squaring up. You're asking, how many states are there? And that's answered by this delta function. But each state is weighted by the square of the wave function. This is what we measure with STM, okay? And so what I'd like to do is sort of motivate this. I'm not going to go through every step because that's going to take the entire hour. I'll very quickly motivate how we get to this. And then if you're interested, I can give you references. And after that, like I said, I'll show you two particular techniques, which is quasi-particle interference and Landau level spectroscopy. Okay, so let's just start. Erasing this. So what is a scanning tunneling microscope? An STM is typically, this is an STM, right? So what is it? This is a tip. It's usually just you take a wire, just cut a wire, little tiny wire, and then this is your sample, and you bring, using piezos, by the way, piezoelectric crystals, you bring this tip really close to the sample within a few angstroms, and at that distance, you are able to tunnel, you're at a tunneling distance, so you're able to tunnel across the vacuum barrier from the tip to the sample or sample to the tip. And the thing we measure in STM is the tunnel current, okay? So that's our only measurement. So we measure I, the tunnel current, and I forgot to add let me just add that. You can measure, you have many knobs, so you can measure current as a function of bias voltage. And by that I mean the potential difference between the tip and the sample. I'll tell you what happens. So basically, when you're far away, the Fermi energies of the two are different. When you bring them close together to the distance at which they can tunnel, the Fermi energies of the two will equilibrate, and you get zero tunnel current. And then you apply a tiny potential difference between the two, and you start getting tunnel current again. And that's the tunnel current that we measure. And that tiny potential difference is provided by this bias voltage. So you can measure current as a function of bias voltage. You can apply magnetic fields. You can measure I as a function of Z, the distance between tip and sample. You can sweep the tip across, raster the tip across the sample and measure the tunnel current. You can functionalize the tip. You can make it magnetic. And then you get magnetic information. You can, get information about whether your surface has an upspin or a downspin. So you do many different things with STM. Yes?
If you add a magnetic field, do you resolve momentum information because you're giving the electrons a kick?
Yeah. So I'm going to answer your question. We do not get the electrons go in circles. The magnetic field we apply, we could apply an in-plane field, but not many people have that capability. I'm going to apply out-of-plane fields, and then you get cyclotron orbit, and you get Landau levels. Okay. Yeah. Okay, and I'm going to talk about that.
What does it mean for the experiment? Do you have to be if you move a magnetized thing, you should induce electric fields, so do you have to wait all the time after?
Yeah, so this is a good question. So you have to, I should have mentioned this. Think of STM as a quasi-static probe. We actually move very slowly on the scale of the equilibrium time of electrons, which is femtoseconds. We just take our own sweet time, and we move millisecond time scales, raster the tip, I mean. Also, yeah, so everything we do is quasi-static, and think of this as a quasi-static experiment, static if you wish. Apply a magnetic field, park yourself at a particular point, and measure density of states. And then you move to the next point, measure density of states, you move to the next point, measure density of states. So, static experiment.
But has then the magnetic field at the surface? I mean, yesterday we heard in the talk that how crazy strong these effective fields are that you get for a thin film. Is there locally also a drastic effect if the tip is magnetized?
Oh, okay. So typically we do STM with non-magnetic tips. Okay. And we do sometimes use magnetic tips, but the magnetic tips we use are very special. We try to have tips which have very, very, very small moments. For example, a magnetic tip we might use is chromium. Chromium is antiferromagnetic. So why does that give us any magnetic signal? Because the last atom on this tip would have some particular orientation of the spin, and that is what gives us the magnetic signal, but the net magnetism is zero. So those are the kinds of things we use, yeah.
Thanks.
Okay. All right. So this is how STM works. So how do I get the formula I wrote down earlier? Let me just sort of motivate that. So we also draw these kinds of pictures for STM. So far away, we draw the sample and the tip as potential wells of electrons. So far away, they have some different. This is the Fermi energy. So let's say, which one? This is, let's say this is the sample, and this is your tip. So far away, they're little buckets of electrons, and the Fermi energies are at different positions with respect to vacuum, right, which is 0. You bring these two close together, and of course, once they're in tunneling, once these two, the tip and the sample can tunnel, the Fermi energies line up, right? This way. Okay, the Fermi energies will line up of the sample and tip, and as soon as this happens, there's no more tunneling allowed, there's no tunnel current. And now you can apply a potential difference between the two, and then you move the Fermi energy of one with respect to the other, let's say, So this is your potential difference, EV, and here's your Fermi energy of your tip, and here's your Fermi energy of your sample. Right? You've applied a potential difference, and now you can easily see that you can now tunnel electrons from the filled states of the sample to the empty states of the tip. Right? You couldn't do that earlier because of Pauli exclusion. You can't tunnel states from filled states to filled states. So this is the picture I want you to keep in mind. By keeping this picture in mind, you can also immediately see that this tunnel current, right? You can imagine that this tunnel current should be proportional to the integrated density of states of both the tip and the sample from here to here. So the integrated density of states from the Fermi energy to EV, you integrate that for both the tip and the sample, and that should be proportional to your tunnel current. Okay. Yes?
But this means that then probably the tip has to be something like very simple or at least controllable so that you kind of know what...
Yeah. This is a big problem in STM. One of the big problems is it's agnostic. It doesn't matter, we get signal from both the tip and the sample. So if you want to isolate the signal from the sample and make sure that your spectroscopy is not being wildly affected by the tip density of states, you have to make sure that your tip is benign, meaning that the density of states of the tip should hopefully be constant for a large range of energy across the Fermi energy. In that case, anything you see comes from the sample.
I guess a similar problem than when you have leads and they have to be kind of, like when you're trying to connect a sample and try to have some transport, the leads have to be basically very simple in order to not influence.
There you have other problems as well, band bending and so on, yeah. Fermi velocity mismatch, all kinds of problems. Okay, so you have to have a benign tip, yes.
So the density of states needs to be constant with respect to the energy?
Fermi energy on either side of the Fermi energy, yes. So the tip is a three-dimensional object. What ends up being the tip, and I'll show you this in a few minutes, because the tunnel current is exponentially sensitive to the distance between the macroscopic tip and the sample, the thing that contributes the most to the tunnel current is whatever is at the end of the tip, because there's an exponential sensitivity. Moving something by half an angstrom will change the tunnel current by a lot. So let's say you have some macroscopic tip like this. At the end, you have a few atoms. And the thing that contributes to the tunnel current the most is this atom at the end. Okay? And so what was your question? That it's a flat density of states, yeah. So what we do is we can prepare the tip on another metal, and which also has a flat density of states, like copper or gold. We know these have flat density of states across the Fermi energy. You take this tip that you'd like to use, you go on this metal, make sure that the tip density of states is flat. If it's not, you can play games, you can apply an electric field, things will drop off the end. You can poke the metal if you want, and you just make sure that the tip density of states is flat before you use it. That's good? Yeah. Uh-huh.
Why is it for gold flat?
So we're talking about, remember, we're talking about states very close to the Fermi energy. Mostly we're interested in 100 MeV, 200 MeV around the Fermi energy. So for metals, typically, there's not much going on close to the Fermi energy. We don't usually use gold, by the way, but that's a different reason, yeah.
When you apply voltage, do you also charge the tip versus the system? So do you charge the system? Do you
No, this is a really, so he's asking if we charge the system. The answer is no. Charging is a big problem. If we charged, then the voltage we apply and the voltage that actually gets transmitted would, seen would be different. In fact, we can see charging because then if you change the distance between the tip and the sample, then everything will change because the electric field will change. Mm-hmm. So we don't like charging, and so we make sure our tip is metallic. And unfortunately, that means we are constrained to mostly conducting samples. Of course, we would also crash. That's a different story. But we do sometimes, in samples that are not very conducting, we do see charging, like graphene. Mm-hmm. And that you have to take that into account. But we don't usually look at samples like that. Yeah. OK, so yeah, we don't have much charging going on, or we have no charging going on. OK, so let me just show you, motivate that formula that I wrote down earlier. So the way, it's really not very complicated. It's basically time-dependent perturbation theory. What you do, and you end up with something that looks like Fermi's golden rule. Okay, that's what it is. So what you do is you say that far away from your, when the tip and sample are far away, you just write down, you just say, your tip and sample wave functions satisfy the Schrodinger equation. And I should really be writing del squared, but just for my simplicity, I'm going to write that. Oh, yeah, so where I can be sample or tip, right? These are this is your sample, this is your tip. You have the Schrodinger equation. Let's say you're a supercomputer and you can solve this for your tip and sample and you get the wave functions. Okay, so there are these things have some eigenstates, right? So the eigenstates would look like psi mu I e to the minus I e mu I t over h bar, where if I is s, these are the sample eigenstates, and if I is t, these would be the tip eigenstates. Okay, so now when we bring these two together, then of course we have a different Hamiltonian. So now we have this new Hamiltonian. Right? And now in theory, it would be nice if we could simply solve for the wave functions, and then we would know everything. But of course, in practice, that's not possible. So we can ask a very simple question. We can say, far away, this is our Hamiltonian. We know the solutions to our Hamiltonian. We know the tip and the sample eigenstates. When we bring them close by, close together, we can ask, let's say we start with an electron in a particular eigenstate of the system, psi mu, and we can ask, what is the transition probability to the tip, to an eigenstate psi nu on the tip? We can ask that question. And that this answer to that question is given by time-dependent perturbation theory, right? So what you say is, think of the sample with this Hamiltonian, right? These are the sample eigenstates. And then you say you have the tip is a perturbation, okay? And then in the presence of the UT, the tip perturbation, your new eigenstates will be your old sample states plus a mixture of the tip states. Okay, so that's your ansatz for your new states. So you say that psi equals A mu. Remember, we're starting with an electron in state psi mu s. And then in the presence of this tip, this is time dependent. I mean, this should be bringing back memories of time-dependent perturbation theory.
You're treating just as an external field. We're not thinking of any interaction between them.
Yeah,
It's just an external.
just a perturbation that takes your original state, and there's a finite probability of transition to the tip. This is what you do. So what you do is you turn on your tip. You write as a time-dependent sort of perturbation. So you say U is eta, some ut e to the eta t. So I just want to make sure I don't, there's some positive and negative signs here. Over h bar. Right? So you just temporarily start with this kind of a time-dependent perturbation. You say that this is happening very slowly. This is true, that when you bring the tip in to tunneling, it happens over a very, very slow time scale compared to femtoseconds. And then what you do is that at the end, you set t to infinity. Oh, eta to 0. Yes?
The sample eigenstates, are those delocalized block states, or are they somehow like localized in the same area as the red atoms?
So let me show you what we just again, another really nice picture to keep in mind is this one. So along with having these buckets of states, so let's say this is your sample, this is your tip. Your sample states do that, and your tip states also. So these states are any state that comes to the surface. These could be surface states of the sample. These could be bulk states that come to the surface and decay into vacuum. We'll measure all of it. Okay, we're not, all we need is for the state to come to the surface and decay into vacuum. Once there's a state that shows up at the surface and decays into vacuum, we'll measure it.
Yeah, okay, thank you.
Okay. Okay, so that's basically it. So this is your ansatz wave function, and now you do what you do for time-dependent perturbation theory. You insert, oh, did I just erase the, yes. So you insert, that ansatz wave function into this full Hamiltonian. You project it. Then project this onto one of the states, and then psi mu, let's say, and look at first order. And to first order, you'll get something like this. So remember, you've projected to psi nu. Okay? All you've done is taken this ansatz wave function, put it into the Schrodinger equation, and projected to psi nu. Okay? And kept only the first order terms. And then you can integrate, you've done this many times, this is just perturbation theory. You just then integrate this, right? And so if you integrate it and square it, you'll get c nu t squared. where this is the matrix element M mu nu. And so the tunneling probability is just the derivative of this. Right? What is this tunneling probability? The tunneling probability is you start with this electron in state mu on the sample, and the C mu t gives you the probability of tunneling into a state nu on the tip. Okay, and that is just this, and that's equal to and now, like I said earlier, you want to turn off the time dependence. Everything's come to equilibrium. So you take this eta to 0, okay? And when you do that, you see that the tunneling probability gives you 2 pi over h bar delta E mu sample minus E mu tip times M mu nu squared. So already this has all the elements you need, right? Okay, so this is just Fermi's golden rule, sort of. This has all the elements that you saw in the formula I wrote down earlier for tunnel current. First, you have this delta function. Of course, this delta function is not yet the density of states, but once you work through everything and you put on the Fermi function for finite temperature and you change variables, you'll get 2 delta functions out of this, one for the sample and one for the tip. That tells you that you have equal energy tunneling. The second is this M mu nu is this matrix element. And this matrix element, what you can do is there are very simple approximations. For example, you can take the tip and say that you have just a very simple S-wave tip. And so you know the tip wave function is very simple. And then if you use that approximation and just a few very simple approximations, you'll get that this reduces to simply the square of the sample wave function and the tip wave function, of course, which can be removed. So then just going from here to the tunnel current is a pretty simple exercise. Okay. So this is how you get the formula that I wrote down earlier for the tunnel current, which is that. And so I'm going to use that as a starting point. So I di dv, right? You take the tunnel current and you it's S, let's okay, assuming that the tip density of states doesn't matter. So this is my density, the derivative of my tunnel current. So so do you understand how? So you take this. Of course, this is for tunneling from one state to another state, mu to nu. You integrate. You add up all the states, right? And then you apply the Fermi function, and eventually you'll get to that. Okay, so let's ask what does this mean before I go into my PowerPoint. So there are 2 components here. One is this one. So when we measure di dv, which is the thing we usually measure, the differential. So remember I said we measure the tunnel current. You take the tunnel current and you differentiate it with respect to bias voltage. That's di dv. When we measure that, we get two things. One is, if you sum up if you ignore this for a second, psi squared, and why can we ignore it? Think about some plane wave e to the ikx. Psi squared is a constant. So you can just ignore that for a second. And then if you do that, the sum over all these delta functions is just the density of states at a particular energy, right? Is everybody familiar with that? Okay. But then that's one part of the story. But then the other part of the story is that we have the psi squared. So for some reason, if the psi squared has information, then we can pick that up as well. So when does psi squared have information? One possible place it could have, there are many places, for example, a charge density wave. If you have a charge density wave, then psi squared would be inhomogeneous. You would see more charge in one place and less charge in the other. After all, psi squared is just charge. And so you'll see that in STM, okay? But more than that, if you have some scattering from some impurity, then you just think about it in one dimension. In one dimension, you have some incoming wave e to the ikx, which of course squares to 1, which is not a problem. But if you have a scatterer, then you have a scattered wave e to the minus ikx. And in this area, you have the eigenstates are a sum of those two. And now when you square that, you'll get structure, because it'll look like cosine 2kx. And now suddenly in STM, you'll start seeing waves when you have impurities that scatter electrons. Okay? So, yes?
But you probably can't resolve some of this magnetization like an interferomagnet, right? Because we sum over the...
So I think you should forget about spin for temporarily, because many of the systems I'm going to show you don't have the spin degrees of freedom are not very interesting, right? Because the ones I'm going to show you are topological insulators, topological superconductors. And of course, if you want to talk about antiferromagnets and ferromagnets, then you're interested in the spin degree of freedom. But for that, we would use a spin polarized tip, and I just don't have enough time to show you data with a spin polarized tip. So just leave spin out of your mind. Yeah, just forget about it. Just think of it as a factor of 2. Okay?
I'm just a bit with that ansatz. I was just thinking about it the whole time. I just have a question.
Oh no.
Is there a reason why we can't have the terms when I transition to the other eigenstates of the sample? Because in principle, I start with the one eigenstate of the sample, then I have the sum over the eigenstates of the probe, but in principle, I could also transition to the other eigenstates of the sample. Or is it just that those transitions are much harder?
Yeah, so sure, you could mix, in the presence of the tip perturbation, you could mix the eigenstates of the sample, but traditionally in STM, the tip is such a tiny perturbation that we don't consider, we think of the sample eigenstates as being undisturbed by the tip. If the sample eigenstates, so the tip electric field, for example, if it's a reasonably good metal, is very well screened. Of course, screening implies perturbation, but we typically think of the tip as not perturbing the sample. If a tip started perturbing the sample, we would get into trouble, because then we wouldn't be measuring the sample itself. Yeah. So we're pretty far in terms of, so we're a few angstroms away, let's say 5 angstroms away. So yeah, I mean, that we take trouble. So for example, that is why you don't want a very magnetic tip. You don't want to use a ferromagnet as your tip, because then the spins on the ferromagnet will affect the sample that you want to study. Yeah.
So basically, in principle, you could write those other terms.
We could.
So much smaller that we kind of take.
That is what we assume. It's an assumption. It's an assumption. Yeah. Yeah. Okay. All right. So now let me go to STM and show you some. How do I move this out of the way? Just pull, push.
Yeah, I think maybe there's
Okay. Oh, all right. Okay, so this is the cartoon of a scanning tunneling microscope, right? And you can do a lot with an STM. So so that's your tunneling electron, and that's the tunnel current that we measure. It's a very simple circuit. By the way, the tunnel currents we get are nanoamps or picoamps. So what we do is we take the tunnel current, and as soon as we can, we use something called a preamplifier, which is both a current to voltage converter as well as it has a large gain, right, of 10 to the 9 or 10 to the 12 or something like that. So then we take the current and turn it into a voltage, and that's much better for noise. Okay, so typically the STMs that I use are low temperature systems. So here's the STM again. And also our STMs are all in ultra high vacuum, and that's because we're very surface sensitive, and so we use vacuum to keep our surfaces clean. And our experiments are done at low temperatures, 4 Kelvin, and the lowest temperature we can get to is 300 millikelvin. And because the STM, the tip is so close to the sample, a few angstroms away, we want to minimize perturbations like noise from the floor, vibrations, as well as sound. So everything is mounted on, what happened there? So everything is mounted on pneumatic springs, meaning just everything is floating on air essentially, and also everything is enclosed in a soundproof room. Okay, so this is all very important to us. Okay, so this is what the STM looks like. One of our STMs. So here you can see the UHV chambers. And this is a table. This is actually a granite slab, and the reason for it is that the granite slab is thousands of kilograms, and it actually lowers the resonant frequency of the air springs. The larger the mass, the lower the resonant frequency. It brings it down to about 2 hertz, and so everything above that is damped, and that is why we need this heavy mass. And then here's another STM. This is a 4 Kelvin system. This is a 300 millikelvin system. And down here, you can see is a dewar. You can barely see it. These are the air springs, by the way. Down here is a dewar, and deep inside that dewar is the STM. So this is what one of our STMs look like. All our STM heads are commercial. They're from a company called Unisoku in Japan, which is why everything looks so nice. I've built STMs before. Mine never looked like this. It's actually pretty small. It's this is about 1.5 inches, or even less than that, maybe 1 inch. So you can think of the scale. It's a tiny thing. So up here, you see there's a thing on the side. I don't know if you can see it. It's a stainless steel object which is on its side. We had to open our system because the sample had fallen on its side, which was very sad. Anyway, this is where the sample sits, and in here, you can't see it, is the tip. Okay, so we can, this is what I was telling you before. You should always keep this picture in mind when you're thinking of STM. You have a bucket full of electrons, that's the sample, another bucket full of electrons, that's the tip. You apply a potential difference between the 2 electrons, and of course you can also raise the tip potential with respect to the sample. Either way, electrons tunnel from filled states on one side to empty states on the other, and that's the tunnel current that we measure. One thing that I forgot to tell you is that this tunnel current, actually, so in my derivation, I didn't mention this, that matrix element that I wrote down, you can show that matrix element gives you this kind of an exponential factor, but this really just comes from the exponential tails of wave functions. So all wave functions that reach the surface die exponentially into vacuum. So you have an exponential tail of wave functions from the sample, another one from the tip, and when those two overlap, you get a tunnel current, and so the tunnel current is exponentially sensitive to the distance between the tip and the sample. So we use that exponential sensitivity to get images like this. This is actually the image of a topological insulator, a bismuth selenide. You can see the hexagonal arrangement of atoms. These are selenium atoms. Each of these things that you see here, including these bright, extremely bright, large dots, is a single impurity. So remember, on this scale, a single impurity would be the size of this little atom here, but each impurity has a large effect on the local density of states, and that's why it looks so big. How much time do I have?
10 minutes, 15 depending.
Oh my God, okay. That's bad.
Maybe a bit more, actually, because we started a bit.
Yes, okay, good. All right, so this is what I meant. This is what we measure. This is the tunnel current. It's integrated from 0 to the bias voltage of this quantity, which I kept writing down. And then when you take the derivative of this with respect to voltage, you get this thing. We call this whole thing the local density of states. So then the sum over all these delta functions, ignoring this part, would be just the density of states at a given energy. But of course, you have this wave function as well. Okay, so what can we do when we measure dI/dV with respect to energy? For a metal, you would get a flat density of states. That's why it's a metal across the Fermi energy. And remember, for us, 0 is when the two Fermi energies line up. So 0 bias is actually the Fermi energy of both the tip and the sample. And then if you were to measure a conventional superconductor, an S-wave superconductor, you would see this. There would be no single particle states inside the gap, so 0 density of states. And then right at the edges, you would get these tall coherence peaks. And so this is what, this is what a spectrum on BISCO looks like, bismuth, strontium, calcium copper oxide. It's a high-temperature superconductor, and you can see, look at this energy scale here. It's hundreds of millivolts. This gap is really large. It's about 30 to 50 MeV. This is 45 MeV. You can see these tall coherence peaks, but you can also see that there is density of states inside the gap. So this is not a conventional S-wave superconductor. The S-wave superconductor would have no density of states inside the gap. This tells you that you have excitations inside the gap, and that's because the gap in this case is a D-wave gap with nodes.
Do you have an example for something else than Fulge?
Sorry?
Do you have an example how does it look when there's a Fulge?
In BISCO, no.
No.
Oh, yeah, I do, but I don't have it on my computer. Yeah, I can show you.
So when you say it goes to 0, this is 0 to what level? And what's the ratio between the normal and the 0?
Okay, so I'll tell you how we determine that. It's not a good thing to look at dI/dV. Better to look at IV. And it's the slope of the IV, right? So how flat is it, you're asking? So you compare that to the noise. So you have some noise and you have some slope, and so it's much flatter than the noise usually. It's just like for an S-wave superconductor.
If you compare to the normal...
it's a huge, it's huge.
1,000, factor 1,000 or even more?
This is a very typical factor for us, not a factor of 1,000. This is very typical, but I don't even know how to. I can think about that. I don't know how to quantify that. Okay.
So you say this looks different from S-wave?
S-wave, because this is a D-wave superconductor and it has nodes. That means that there are certain directions in momentum space where the gap actually goes to 0. And that means that in those directions, of course, you have quasiparticles, and that's why the gap looks like this. And also, the gap is not homogeneous. It's actually looks like a clover. Yes?
Yeah, there are shoulders away from the coherence
This?
peaks. Yeah, and then
Oh, this is a huge field worth 20 years of research. Essentially, there are many possible explanations for this. One is that it's electron-phonon coupling. And we see electron-phonon coupling in STM through a different channel. It's an inelastic channel. So everything I've been talking about so far is elastic, meaning the electron energy on the tip is the same as the electron energy in the sample. But you can also have an inelastic process where the electron, as it's tunneling from one to the other, actually kicks off a phonon or a spin wave or something like that. And that inelastic process also gives you signatures in the tunnel current, which looks like steps which are symmetric on either side of the Fermi energy. And so this could be an inelastic tunneling process. Another possibility is that because there's electron boson, whatever the boson may be, coupling, the density of states is actually modified. There's the Green's function is modified, and that shows up here as well. Both things would show up, and so there are many possible explanations for these features. There's more than one feature, by the way.
Could you give like the form of the shoulder? Does it give you the information like what might be the process?
Yeah, exactly, it does. Unfortunately, in this particular system 2212, a phonon and a magnon, or a magnetic excitation, are very close in energy. So it's hard to tell. I believe actually that this is actually a phonon. So there is some strong electron-phonon coupling. You can track this as a function of temperature. And then you can track this as a function of temperature, and you might be able to ask if it sharpens or not and stuff like that. Yes?
You said that you can see that. You said that we can see that it's not S-wave because the density of state doesn't go to 0, right?
Yes, also it's not straight. See, there's a curvature here.
But what if it's not S-wave but still gapped superconductor? Can you see that? Can you differentiate?
This is S-wave, but and not. What do you? Sorry.
You measure a sample which is gapped superconductor, but it's not S-wave, so will you be able to
for
tell the
example,
difference?
Fully gapped?
Yes.
PX plus IPY. Yeah, sure. How do we know the difference between an S wave and a P or some other order parameter? There are many techniques we have. One of them is we can actually measure signs of the gap. Yesterday or day before, someone was talking about S plus minus. Yes. In ion selenium in ion-based superconductors. We can measure that in STM. But I'm going so slow. I hope to get to, let me at least get to quasi-particle interference, and then we use that technique to measure things like that. There are many things we can do, actually. So STM is not only about imaging and spectroscopy. It's much richer than that. That's what I'd like to show you. OK, so this is an example of data sets. So here's spectra at a few different points. You don't see the blue one. There are 3 of them, actually. So red is at one point, and B is at a different point very close by. They're completely different. So if you were to plot the density of states at this energy as a function of position, it would look like this. So we often plot things like this, DI/DV maps, we call them. This is real space location. And so it just tells you right here, red is high. So this area has tall coherence peaks. Somewhere here in this region, you would have very, very short coherence peaks. And so we plot DI/DV maps like this. So these are the kinds of data sets. We plot topographies, spectra, and DI/DV maps. OK, so let's talk about quasi-particle interference. I already alluded to this. Usually, psi squared doesn't give you any information. But if you have a scattering center, then you can have an interference between the incoming waves and the outgoing waves. And that interference process, just in 1D, you can see that interference process should give you psi squared that looks like cosine 2kx. So just to give you an example, so here's a surface of copper. The surface of copper 111 has surface states. The 2-dimensional gas of electrons that has a very nice quadratic dispersion. This is not looking quadratic, but it has a nice quadratic dispersion. So this is ARPES data you can see at some given energy. This is what the states look like. And then when we do STM, I take a DI/DV map at this particular energy, which is 30 millivolts below the Fermi energy. You see all of these wave-like patterns, and this is precisely what I said. This is the interference pattern. And now I can take a Fourier transform of this, and it looks like this. So this Fourier transform, the radius of this is actually 2k, OK? So that means that if I were to plot, take DI/DV maps as a function of energy and plot the energy versus this radius, I should get the dispersion, right? And so here's the data. So let's say I'm going to now go from the bottom of the band and show you the Fourier transforms as we get to higher energies. And you can see that the size of the circle actually gets bigger and bigger and bigger. And that's dispersion, right? And now I can plot the size of this circle as a function of energy. This is actual data, and the error bars are much, much smaller than these circles, by the way. And so there you go. This is the parabolic dispersion. By the way, we fitted this, and not only does it actually fit ARPA's data perfectly, but more than that, if you look very close to the Fermi energy, amazingly, you'll see little wiggles. That's electron-phonon coupling. You can see the wiggles due to electron-phonon coupling from this quasi-particle interference. You can even you can invert those wiggles and get the real part of the self-energy due to electron-phonon coupling using this technique. So this is a very, very sensitive, our energy resolution is very, very good. Yeah, no, we don't call it, we shouldn't be calling it quasi-particles. It's just electrons. It's historical. So there were experiments that were done many, many decades ago, but then Seamus did the first experiments actually getting the dispersion and plotting it, but this was in a superconductor. So obviously there he called it quasi-particle interference. So the name has stuck. It's just electron interference for copper.
What's the energy resolution you get?
Our energy resolution is set by our two things, temperature and the modulation that we use. So at 300 millikelvin, we can get microvolts energy resolution, not 10, maybe 20 microvolts or something like that, yeah. So it's pretty good. This was taken at 4 Kelvin, yeah.
Can you measure the width of the levels at high energies, the electron-electron scattering rate?
So
In principle, to be somewhere there.
we have not, that's something I've been wanting to do for a long time. We haven't done it yet. So I really would like to do that. We've measured the effect on the dispersion, but I've been trying to think about in the Fourier transform, does that width also have information, and that I haven't done yet. Yeah. Okay, so now let me just go to what I really wanted to show you, which is STM studies of TCIs, which are topological crystalline insulators. I'm going to really try to go quickly through this. Unfortunately, this means I'll have to show you this very quickly tomorrow and then talk about topological superconductors. How much time do I have?
It depends how many questions, but 5 minutes?
Yeah, okay, 5, 10, okay. Okay, so this is I'm going to show you two things on topological crystalline insulators. One is the quasi-particle interference. I want to show you that and show you how you can get some very nice data. But then I want to turn on a magnetic field and look at Landau levels and show you what kind of information you can get from Landau levels. So topological crystalline insulators are, of course, a topologically non-trivial class of materials. They're just like TIs, except rather than having time reversal symmetry be the symmetry that protects your Dirac point, here the Dirac point is actually the symmetry of the system is mirror symmetries. So if you, for example, if you broke mirror symmetry in the system, you would grab out the Dirac point. It's very similar to TIs, except that instead of having the, in TIs you want to have an odd number of Dirac cones inside your Brillouin zone. Here you're allowed to have an even number of Dirac cones in your Brillouin zone. Okay, so the material I'm going to show you is lead tin selenide. And the interesting thing about this material is that as a function of tin content, you actually undergo a topological to trivial phase transition, which is really beautiful because now I can track what happens to the surface states as you go across this transition. Okay, so I hope to show you data about that. So this is what the crystal structure looks like. Let's say you cleave this. It's a sort of sodium chloride crystal structure, rock salt. When you cleave this, you expose this lead and selenium plane, and you can see you have both lead as well as selenium atoms, right? It's an interpenetrating lattice. But the thing is that when we do STM, we only see the selenium atoms. We don't actually see the lead atoms very clearly at low bias voltages. So this is the square lattice we're going to see. So this square lattice, these atoms are actually these atoms, and the atoms in the middle, at least at low bias voltages, are not very visible. As you go to higher bias voltages, they actually become visible. And the fact that you can't see them at low bias voltages is actually going to be important for something I'm going to show you later. So this is what the density of states looks like. It looks like a superconductor, except don't be fooled, here's 0. So the spectrum should be around 0 if it's a superconductor, right around the Fermi energy. Here, this is actually negative 70 millivolts. So why does it look like this? It looks like it has a gap, but actually it doesn't. So this actually turns out to be coming from this is the dispersion of the system. This is what the band structure looks like. So you have this linear dispersion right around the Dirac point, and that's what gives you that V shape. And then those little coherent peaks-like objects are coming from this flat portion right here, which is known as a Van Hove singularity. So basically comparing this to this flat portion of the surface state gives you this coherent, this Van Hove singularity gives you the sharp peak in the density of states. And then this linear dispersion, in 2 dimensions, you get a linear density of states in 2D, okay? So that... This is a topological crystalline insulator. And so it's just like a topological insulator, which has these non-trivial surface states. So in theory, and look at this dispersion, it's linear. So in theory, this should be not topologically non-trivial surface states. But the thing is, the data I'm going to show you will actually show you that that's the case. That is, that these electrons actually have Dirac dispersion. I'll show you that. Oh, the whole thing is a surface state. I'm really sorry about that. Yeah, so these are the shaded areas of the bulk states. This is a very nice system. The Dirac point is nicely exposed. And these lines here are the surface state dispersion. Yeah. Uh-huh.
The 0 here is
it's not 0. It's not 0.
It's not 0, so the actual the 0 is to the left somewhere?
Oh, this is the Fermi energy. So no, you mean the DIDV? It's not exactly 0, and I don't know how far from 0 it is. I can't remember. It's not exactly 0, but yeah, that's I'll have to go and look at it and see how. So one of the reasons it's not 0 is there are always some impurities in the system, but then yeah, so it's not exactly 0. Even in graphene, it doesn't really go to 0, actually. I don't know exactly why. Okay, so we can do DIDV maps, and so here's the topography. It's actually a beautiful topography. Those little tiny dots you see are actually the atoms that I was showing you earlier. This is a pretty large scale for us. Here's a DIDV map. You can do, this is what it looks like when you zoom in. You can see the atoms, you can see the map. And now we do now we can do a Fourier transform, but let me just show you what the Fermi surfaces should look like. So if you look at the Fermi surface at high energies, it's just 2 little circles, a larger one with this and a smaller one right here. And then as you go lower in energy towards the Dirac point, you get overlapping circles like this, and then right at the Dirac point, it splits. And the reason for all of this is that this Dirac point is very close to the Brillouin zone boundary. So what happens is at very low energy, it's just by itself. But at higher energies, these two actually, this one and this one, because this one and this one are the same. So this one and this one start to merge together, and then the bands start looking like this. And that's what gives you this Van Hove singularity. So this thing is called a Lifshitz transition, where the Fermi surfaces go from two electron-like pockets to an electron-like and a hole-like pocket. So this thing, as a function of energy, undergoes a Lifshitz transition. Okay, so now what do we expect? We can guess that by doing an autocorrelation of these Fermi surfaces. So at low energies, if you do a Fourier transform, you should get this kind of a pattern, 4 dots. And then at high energies, you should get circles. Okay, so this is a high energy map. And now let me just zoom in here and do this as a function of energy. And you can see the circle, it's getting smaller and smaller and smaller. And now we're getting to the Van Hove singularity, where this thing should undergo a Lifshitz transition, and now we see 4 dots. And you still continue to see 4 dots. And then you get to the other Van Hove singularity. It is very symmetric, actually. But then you should see circles, but you see them sort of, but they're very faint. So this is what it is. This is what you expect. This is what you get. You see these dots, and then you see these circles. The radius of these circles changes as a function of energy, and that's dispersion. But then there's actually a physical reason why this circle is not very clear below the Dirac point, and that has to do with the orbitals in the system, and I don't have time to go into this. Okay. So this has to do with the, it has to do with the orbitals, which is the scattering matrices, because one of them is px and the other is py. The scattering matrix element is highly suppressed, whereas these are both pz, and so that's why we see these as being highly suppressed. Okay. So in any case, we can get the dispersion, but close to the Dirac point where we have those 4 dots, the problem is those 4 dots don't disperse as a function of energy. So we don't have any information on what's happening close to the Dirac point, which is where all the interesting stuff is supposed to happen. So in order to get information close to the Dirac point, we have to use a different technique, and that is Landau level spectroscopy. I don't think I should go into this because I think I've run out of time. Is that true? Yes, so I have run out of time. But I will. What I'm going to do is in the next tomorrow, I'm going to quickly show you Landau level spectroscopy, which is beautiful and powerful, and you can actually see not only the beautiful linear dispersion. Just in case you were thinking of skipping tomorrow's lecture, let me just show you. Let me just show you what the data looks like. You know, I'm driven by data, and I will. This is my favorite. So this is the beautiful linear dispersion that you get from Landau level spectroscopy. And there's a mystery, which is you get extra peaks. And tomorrow I'll tell you what this is all about. Okay.
Very nice teaser. Any questions?
Coffee?
So you said if you pass the if you pass the Dirac cone, so you can't resolve the contribution from the surface state itself, right? Or can you?
The thing is, we see the scattering because these are different pockets. It's inter-pocket scattering that's allowed. But the problem is that these are just circles that are shrinking. And so what we see is just 4 dots, and we can't see the dots change as a function of energy, because it's just shrinking circles around one point. So
okay, but as soon as it's a point, you don't see it anymore, right?
As soon as it's a point, we don't see it. But it's also that because it's these circles are shrinking around a given point. We always see 4 dots, and the radius of those dots is what is going to tell us how big these circles are, which is very difficult for us to see. It's very, very small. So we're not able to plot the dispersion using that.
Okay, so STM wouldn't be able to, like, if you had like corner or hinge modes in a higher order topological insulator, there
are many ways we can get information from STM. One is a question of contrast. So if there's a density of states at one location and no density of states at the other location, then that contrast is huge, and even if the density of states is tiny, we'll be able to see that contrast.
Oh, okay. I see, thanks.
So at this ratio of tin to lead, I guess the band gap is very small. So does this influence the measurement?
The band gap is actually, this particular ratio, the band gap is big. It's, for us, big. It's I can't remember, 40, 50 ME. Oh, no, more than that. It's about 70, 80 millielectron volts. Millielectron volt band gap is pretty big. So, but you know, tomorrow I'll also show you what happens as the band gap shrinks. And oops, I don't want to do this. Okay, I don't want to do this. I don't want to go all the way there because there's all kinds of interesting things going on. But tomorrow I'll show you this kind of data as we go from the topological to the trivial side. And it's actually really interesting what the electrons are going to do, right? What is the surface state going to do as you go? So the band gap is going to get smaller and smaller. The surface state continues to exist. And then there's going to be a critical point. At that critical point, the surface state is supposed to span the entire bulk. And then you go over to the trivial side, and then we still have surface states, but they're Rashba-like. That's what I'll show you tomorrow.
Thanks.
Yeah.
Actually, I have a question.
Yeah.
Has anyone measured QPI on the surface of things that are not translationally invariant, like quasicrystals or things like this?
No.
'Cause in principle, you could do it and see if you have like long wavelength excitations and things like this.
That would be interesting. I have never thought about it. These are, yeah, that would be interesting. We would have to find a system, but yes, I think that would be interesting.
I asked if somebody had measured QPI on quasicrystals. On the surface of quasi. Yeah, but I mean, you could still see, like, if you have a low wave, let's say long wavelength excitation, even if it's gappy, you should see a dispersion that. You know,
it depends.
Yeah, I mean.
Depends on how insulating it is. If it's very insulating, it's very hard for us.
Yeah.
But we are able to see semiconductors. It depends on the gap magnitude. So if it's a few hundred MeV, we might be able to tunnel into it. If it's many electron volts, we have a problem.
Okay. Cool.
You mean above the gap energy? Yeah. So if the gap is that big for some reason, even if you bias above the gap, we still are not able to. The electrons. This is the charging problem. For some reason, in these insulators, the electrons don't leave the vicinity immediately, and then they charge up that local area. So I guess, and so then essentially, we're not able to tunnel anymore, and we basically just crash into the sample.
Okay, maybe we should go to have some coffee and send Vidya again.